All right, we're back. We're going to talk today about intensity and temperature. How you doing, Keith?
Doing well. How about yourself?
Pretty good. Hey, I realized we didn't have a whole lecture set up to talk about FDA, but I thought we would talk about that today.
And something that's really important to note is that if you're designing a device for a research study or for actual medical use, you will inevitably run up against the FDA, and they're here to regulate what makes a device safe. And for us in ultrasound neuromodulation, that comes down to how much heating and intensity is on the brain.
Yeah, that's
So very
exactly right.
important.
Yeah. Okay, so that's perfect lead in. So let's get started. So this is the outline for today. We're going to talk about intensity measurements, highly focused transducers and gain, optimal frequency, and then lastly, we're going to end with electronic steering and mechanical steering. So how do we do intensity measurements? You use a hydrophone. I bet you have, how many hydrophones do you have, Keith?
I have none. I use yours.
Oh, is that right?
Yeah.
All right, well, let's talk about hydrophones. So a hydrophone is essentially a small piezoelectric crystal, or it could be a fiber optic sensor. It is set up in a scan tank, as shown over here on the right. Here's a hydrophone. It's a very small hydrophone here inside the water bath. And then there's a transducer up above. And typically what will happen is the ultrasound will be set up to send small pulses out periodically, and the hydrophone will measure them. It's on a robotic arm, and it's going to be moved around and make multiple measurements. So it looks something like this. All right, and as it's scanning around, then it measures the pressure at each point, and then it can come up with a map, as you can see here. So it can scan around in 3D, you can come up with a picture across the beam or along the length of the beam, as you can see here. And this is really nice. You can see here the side lobes on this single element transducer beam pattern. So
Are these optical measurements that are made? I forget how the hydrophone actually works.
well, it depends. I mean, this is usually small piezoelectric crystal, so it's just transducer picking it up, just like all the other we talked about. Yeah, typically very small tips, so you can get high spectral resolution. Typically, they're very, very sensitive to low pressures. So that's something we'll talk about in just a minute on what that means. They're typically very broadband, and oftentimes you send out a short pulse. If you were to send out a continuous wave, then that would make it potentially more damaging to the hydrophone. So oftentimes very, very small short waves. And they're also very precisely calibrated. Every time we have new transducers, we have a fiber optic transducer hydrophone, and every time we purchase more, they have to recalibrate the whole system, because we really want to make sure we get very good measurements, and so they're calibrated very precisely. All right, so you scan around and you measure what the pressure is. You can convert that, of course, into intensity. For ultrasound imaging, whenever they're estimating what the intensity is deep inside the tissue, they have to take those measurements that they might get in a water bath and then derate them for the situation that they're in. And what they do is just for whatever the beam path is, so the length of the beam, they derate it with an attenuation parameter of 0.3 dB per centimeter per megahertz. And of course, this number, this attenuation number, is much smaller than it is for soft tissue. You can see the table down here, and that's because they really want those measurements to be sort of or those estimates to be a worst case scenario, so that the intensity estimate should be higher than reality, and then so that it's actually less than their measurement, and it's going to be safer.
That's sort of not intuitive for me, because wouldn't you want the worst case scenario to be on the high end of measurements, but you're saying they lower it to make your measurement.
Well, no, that's exactly right. Is that the worst case scenario, that the estimate of intensity is on the high end? That it's
so the derating actually raises the measured value.
Yeah, that's right.
Okay.
So it's a little less clear how to do it for non-imaging applications. So for our neuromodulation interests, we're not really interested in just saying, well, what's the worst case scenario? We're interested in actually kind of getting it right. Because if we don't get it right, we may not actually have an effect at the focus. And what this means is it really kind of ups the our interest in having good modeling capabilities so that we try to get that estimate just right. Better yet, it would be nice if we could have some in vivo measurement of what the intensity is, but there aren't really very good options. So we'll talk about one a little bit later in a later lecture. All right, so a couple of things to keep in mind for hydrophones. One of the things is that CW and pulsed ultrasound aren't exactly the same. So if you're thinking about doing your neuromodulation in CW, and so that's anytime then you have more than like a few cycles, maybe more than like 10 or 20 cycles, and it sort of becomes a CW, then the pulse, the beam pattern actually is a bit different. So these are some simulations that I put together. Here is a CW, and here on the right is just if we did 3 cycles pulsed. And you can see that the beam patterns are a bit different. And you may ask, you have any idea why that might be, Keith?
I would imagine that you would miss some of the grading lobes in the continuous wave or whatever those little side lobes are, but the patterns are actually different, so I have no idea.
Yeah, so these are side lobes. The grading lobes would be bigger and would be further out. But if you think about like sort of the frequency components, if you have CW, then you just have one frequency. And if you have pulsed, then you have a broader band. So there's more frequency components. And so there's the opportunity with more frequency components that there's more interference pattern. And so you kind of lessen those bands out there and kind of that near field stuff because of the interference pattern of the multiple frequencies that make up the 3 cycle pulsed.
So your pulsing would have to be pretty fast there, though. It wouldn't, you wouldn't see anything if you were pulsing like 10% duty cycle at 3 hertz or something.
Right. Yeah, that's right.
Yeah. Okay.
Something else to keep in mind is that the hydrophones really only work for low powers. So if your application is for much higher power, you can scale up your result, but it may not scale up linearly. If your transducer response isn't linear, then you may just not get a good estimate of what is actually happening at the higher power. So that's just something to keep in mind. All right, so I want to talk a little bit about the terminology for our beam patterns. First of all, there's spatial characteristics. So this is our focus right here. And we have, if you take a line drawing, you could draw it either way. It just affects sort of the width of the intensity. So this is a line drawing as a function of space. And of course, you can define the intensity that is the peak. And you can also say, well, what's the spatial average if you're averaging across that spatial pulse. And so these would be the intensity for spatial peak and spatial average. There's also temporal characteristics. So for example, if you're looking at the pressure wave, there's the peak compression point, and then there's the peak rarefaction point. Those aren't necessarily plus minus the same number. Oftentimes they are, if it's a nice sort of linear pulse, but when a pulse maybe goes into a nonlinear regime, they may not be exactly symmetric around the 0 point. So that may be something that we'll talk about a little bit later. Of course, and then if we talk about the intensity, to get there, we take our pressure and then we square it, divide by the acoustic impedance. We have our temporal peak intensity. We have our temporal average intensity. So if you have multiple pulses, then you might define the temporal average as over the whole time period. And of course, then there's a pulse average, which is just the average over the period of the pulse itself. All right, well, when we typically put them together, we'll start out with what our measurement is. So here it's intensity, or it could be pressure, but let's say it's intensity. And we'll start out with our spatial characteristics. So whether it's the spatial peak or the spatial average. And then we end up with our temporal characteristics over here. So that could be either temporal peak, pulse average, or temporal average. So ISPTA is actually really important. It's the spatial peak temporal average. And what we'll see is that that one's really important for heating, which is something that we'll talk about quite a bit. And then lastly, of course, if there's a relationship oftentimes between them. So if you have a pulse that goes on and then it's off for some time, and you define the duty cycle as the percentage of time that it's on compared to the period, then the temporal average is related to the pulse average by multiplying times the duty cycle. So in this case, if this looks like it's about 1/3 of the whole period there, and so you would multiply times 1/3 to get the temporal average. All right, so let's go through some examples. Let's say you have continuous wave ultrasound. Let's say you have pulse duration, that's about 400 milliseconds. Then your temporal average, your ISPTA, is equal to ISPTP. So that's pretty straightforward. Let's say you have a sort of a continuous wave where you have a pulse duration of, for example, 300 milliseconds, and then you repeat it a second later. Then you might say, well, the temporal average is equal to the temporal peak, but then there is the duty cycle sort of, and you can kind of think about this as duty cycle, that it's on for 3/10 of the time. So we're gonna multiply times 3/10. So the temporal average is gonna be lower than the temporal peak. And the reason why we really care about this, of course, is because we're going to see that the temporal average is going to be related to our heating. So there's all this time period when there isn't any ultrasound, and so heat can kind of conduct away. All right, oftentimes with neuromodulation, we're using a series of pulses. So this is called pulsed ultrasound, or PW for pulsed wave. So there's a series of pulses, and then there's a time when it's off. For example, maybe, I'm just using some numbers here. The pulse duration might be 0.5 millisecond. And for example, maybe we use a 50% duty cycle. Then that means the whole period there is 1 millisecond. That would give us a PRF of 1 kilohertz. Maybe we repeat this many times for a total burst duration of about 300 milliseconds. And maybe there's some time when it's off, and then we'll repeat it again. And that's the interstimulus interval. And let's say, for example, it's 1 second. All right, well, now how do we calculate ISPTA? Yeah, go ahead.
I was going to say, when you have your ISPTA and you have several series of bursts, do you take the whole segment or just the burst itself for ISPTA?
Yeah, it's not really totally clear. So let's see if we can walk through this. If you were going to take the whole time, you would say, you would start out with the ISPTP, and then you would derate it with the duty cycle, right? So it's only on for the amount of time as the duty cycle. But then there's also the fact that the burst duration is only a fraction of the total time. And so there might be that additional fraction in there as well. And so that would seriously reduce the ISPTA. But the reason why I say it's not totally clear is that you might be in a situation where you have a pulse duration which is maybe kind of long, maybe about 1 millisecond, and your interstimulus interval is 10 seconds. Then in this situation, I personally think that we just need to count over the pulse duration and not derate it for all that dead time when nothing really is happening. And then our ISTPA equals our ISTP. Wait, did I say that right? Our ISPTA equals our ISPTP. Right, because there's so much ultrasound on during this time, there could be heating during this time period, even during the pulse, and to derate it for the time period after that seems like it's not really fair.
Yeah, it's not only not fair, but it also seems a little dangerous that the FDA hasn't clearly defined this, because, for instance, if you wanted to artificially lower your numbers, you could have a very long burst at a high duty cycle and then just say, oh, and then we shut it off for 10 minutes. So now our temporal average is extremely low.
That's exactly right.
That's
exactly right. And so there isn't really any consensus on this. And so my feeling is that if the pulse duration or the burst duration is long, and how long is long? Well, I don't know, maybe something like 0.5 second, maybe like 0.3 seconds is long, because you could have heating during that time. Or if your interstimulus interval is long, and there I'm defining long as like maybe half a second or more, then probably you should calculate the ISTPA only over the pulse. And then you come up with this equation over here. And then it still has the duty cycle in there. So if you have a 50% duty cycle, you still have that component in there.
And what we're discussing here is one of the main reasons that it's really important to identify the ISPPA as well. So the FDA does have regulation around that. So even if I had something really, really intense for really short, I have to tell you what that little continuous wave looks like as well.
Right. So let's now talk about why this matters in terms of what the bioeffects are, what the FDA limits are for imaging, and then we'll come back for our situation with neuromodulation.
Mm-hmm.
At this point, I kind of just want to introduce the terminology, and then let's come back and talk about it. All right, so when we talk about exposure, there have been some studies, and there was this a series of studies that was done in vivo that found the following results. Then if you plot out the ISPTA, so again, this is the parameter that is relevant for heating. And this is now in milliwatts per centimeter squared, and it's on a log scale. And you plot versus exposure time, and then we see where there's effects and where there aren't effects. So what they found is that there's basically a threshold at about 100 milliwatts per centimeter squared. Below that, there's no effect. Above that, there is an effect. They also found that there was a curve that was differentiating between where there are effects and no effects, but that depended both on the intensity and the time. So let me just remind you that energy in joules per centimeter squared equals the intensity in watts per centimeter squared times time in second. And what they found was that this threshold was about 50 joules. So you can come up with the 50 joules either by changing up your intensity for the same time or changing up the time for the same intensity. Lower intensity for more time or higher intensity for less time had the equal effect.
What were effects defined as here? I forget, or I even asked you this before and I still forget.
Well, there's any number of ways you can look for effects. I mean, you could just look and see whether the tissue looks as if it's, stiff and white, like it's cooked. You could look at the histology, look on H&E
Oh,
histology.
so this is tissue damage, like explicitly.
Yeah.
Okay.
And so just to sort of put this into perspective, when we're actually trying to heat the tissue, so this, when we're treating desmoids, which are soft tissue tumors, it's not going through any bone or anything, it's just going through soft tissue. We're trying to deliver at our target about 500 to 1300 joules per centimeter squared. So let's just look at the 500 joules per centimeter squared. And so we're talking about exposures that are way up here. And so what we're saying is that these 50 joules per centimeter squared is much lower than what we're trying to do clinically. So this is what we need to be concerned with. But this does introduce that concept that it's not just a single threshold at an intensity level, but it's sort of intensity and time that both matter. So let's say you have a temperature, you know what's happening in your tissue. So this is actually a temperature map that was acquired in the brain during essential tremor treatment. You can see a hot spot there. And we might have measured something that looks like this. So the temperature is going to rise while the focused ultrasound is on. And when you turn it off, the temperature is going to decrease. So now the question is, what do you do with a curve like this? Like, what's most damaging? Is it the maximum intensity that was reached, or is it sort of the area under the curve, some integral of temperature and time? Well, since you didn't answer, Keith, I guess I'll just keep going with what I was going to say.
You to come up with this equation?
All right, well, so people have looked at for a long time this concept of thermal dose, and thermal dose takes into account both the temperature and the amount of time it's at that temperature. And so what they've done is they've looked at a number of different situations, both cells in dish as well as in vivo, and come up with this parameter, which is sort of the equivalent, cumulatively equivalent minutes as if it was at 43 degrees. And it's a way to kind of take these different time temperature curves and relate them to each other. So if you can relate all of them to what was the number of minutes that would have the same amount of damage at 43 degrees is kind of what we're trying to do here. And so there's a relationship here. Maybe sometimes it's easier just to sort of plot it out. And what this is saying is that for every temperature, there's a certain amount of time that has the same effect. And this is supposed to be in minutes, but I plotted it here in seconds for not really any good reason. But for the same effect, what you can see is that if it goes up to 60 degrees, you don't have to have it there for very long, a fraction of a second, to have sort of the same damaging effect as at lower temperatures. So let's say you only raise it to about 52 degrees. Well, then it needs to be there for about 28 seconds to have the same amount of damage. If you've only raised it to about 47 degrees, it needs to be there for about 15 minutes. So this is a nonlinear relationship and takes into account both temperature and time.
And the reason they chose 43 degrees as the center temperature, was that arbitrary, or is there a reason for that?
Yeah, I'm not quite sure about that. That's sort of the upper end of what you might have when your body has a temperature. It's sort of at the upper end of kind of what's normal and where you start to see damage over long periods. So I think at 42 degrees, you don't really, it's really kind of, it takes, very long time.
Gotcha.
All right, so that's the concept of thermal dose. So it brings into the idea that that we'll bring up again and again, sort of, is temperature and time. Temperature can be very damaging. It's not just sort of a single intensity threshold, but temperature and time. Getting back to the FDA limits, these are limits for imaging that were set back in 1992. And the limits that they set for imaging were that the D-rated ISPTA had to be less than 720 milliwatts per centimeter squared. And the D-rated ISPPA had to be less than 190 watts per centimeter squared. Sorry, this is in milliwatts, and then this is in watts. So of course, if you're going to do imaging, your pulse average is going to be much larger, because you're going to do a pulse, and then you're going to do the rest of the image, and then you're going to come back to that area. So at any one location, that's much, much lower temporal average, because there's all that time period that you're imaging other parts of the image. All right, so where's that on this plot? So of course, we have to just make sure we get this right in terms of our scaling. And so it's just a little bit less than 1,000 milliwatts per centimeter squared. So it's about here where the star is. So it's down here with the no effects observed. But that's only if you image for kind of a short amount of time. If you were to image at about 10 minutes at that same location, maybe not so clear. Maybe you wouldn't, not sure what would happen there. All right, so that's what the FDA limits are. There are more stringent limits for imaging cardiac tissue, fetal tissue, and ophthalmic applications. Do you think of a good reason for that?
I suppose there's something about the sensitivity of these tissues to temperature changes that, is unlike bone, where it might not matter that much. Just a guess.
Yeah, I think for fetal imaging, you're always going to be more careful for fetal imaging. I don't know if the fetus is more sensitive. I mean, certainly it's dividing very rapidly, so it's entirely possible. The ophthalmic applications is very clear, just because in the eye, there isn't very much perfusion. And so you just want to be super, super careful and have low intensities where you're not going to have any perfusion that's going to take away the heat.
Mm-hmm. But it's maybe important to remind everyone that none of these were based on neuromodulation, except for, maybe some of the tissue ablation things, but not for reversible changes. So our field is kind of uncrafted a little bit in this regard.
Yes, and so you raise a really good point, is that there really isn't any FDA requirements for neuromodulation. And because there isn't any, all we really have to rely on are the imaging FDA limits. And so right now, the goal is for most people to try to do their studies within these limits that are the limits for FDA, for imaging. But it's not clear that these are necessarily what we're always going to want. And so we're going to have to, at some point, the field is going to have to try to resolve this with the FDA.
Right, but for now, explicitly, if you're a young engineer and you're trying to develop something, just use these for now, I think, and see what the FDA says, right?
Yeah. All right, so let's talk a little bit more about imaging. For imaging, they defined the thermal index, TI. It's one of the safety metrics, again, 1992 standard. The FDA said that they needed to provide this metric on their ultrasound images. So the TI is defined as the time average power that's emitted into the tissue, and then divide by the power that's needed to raise it by 1 degree C. So essentially, if you put in enough power that's going to raise it by 1 degree C, then you get a TI of 1. If you put in twice that, you'll get a TI of 2. So it's going to take into account the power, the frequency, the beam area, the attenuation, et cetera. And the FDA says they need to stay under 2. They don't actually need to report it if it's not less than 1, but I'll show you some images in just a moment where it is reported on the commercial ultrasound system. Of course, this is always true for ultrasound imaging. You want to use as low as reasonably achievable power levels. And then it often is split out into TI for soft tissue, whether there's bone in the field of view, and then for the cranium. But I'll show you some images right now where we're going to looking at this.
Tim, real quick question on the last slide. For W degree, is that the power needed to raise by 1 degree over a long period, like when it hits the steady state? What is that in reference to?
Yeah, I don't know whatever that period is. I would say over a few seconds, probably. Yep. All right, so this is a typical ultrasound image. And up here we have the annotations for safety. I said that before that we would talk about that later, and later is now. So we have the MI, which we haven't finished. We will talk about that later. And here we have the TI. And in this application, this is the abdomen, and we see the liver right here. We see the TI is 1.9. Here's some example images and some phantom. Here we have the exact same setup in these two. And the only thing that we've done differently is we've changed the depth. So here it's a little bit deeper, about 3 centimeters, 1 centimeter over here. And our TI has changed from 0.3 to 0.1. So it's gone down as our focal depth is closer in. It was nice that we had this comparison because everything else is the same. The frequency is the same. We're using harmonic imaging and everything else is the same. Any ideas, Keith?
For
why it's a lower TI to the second image than it is for the first image?
Oh, yeah. So I would guess that they're just using more power to get more reflection intensity at the depth that they need.
That's my guess too. More power is needed to get to that depth. All right.
It's interesting that the second image doesn't correct for it quite as well, though. Like that gradient should be corrected for by the software, but it just didn't in the second image.
Yeah, the time gain control is not set all that great, so there's a loss of signal down here. All right, so there's some in vivo images. Here we have kind of a large field of view, large depth, and we see TI is 1.9, and here we see a lower depth, and the TI is 0.2. All right, so what should we report for neuromodulation? Sometimes you see papers where they were going to report their parameters in terms of pressure, and sometimes you see it where they report the parameters in terms of intensity. And so which one should we be reporting? My feeling is probably not, right? So we haven't had a chance to talk about it, but the temporal peak pressure is going to be related to mechanical effects. And then there's the intensity, and we've defined a number of different intensities, but the ISPTA is the one that's most relevant to heating. So my feeling is that we probably should report both. And the argument against that is that, well, they're related to each other. All you have to do is figure out what the temporal peak is, then you can square it, divide by, and figure out what your intensity is and account for that. But it just makes it a lot easier for the reader and the reviewer if they have one parameter that's reporting something that's related to mechanical effects and one that's you're reporting that's related to the heating possibility. And while they are sort of redundant, if you explain the timing of your ultrasound pulses very well, sometimes it's a little unclear what the timing is. And so going ahead and reporting both those parameters, I think is probably easiest for the reader and the reviewer.
And everyone should know that these parameters are often like left out and everyone uses very different things. And the reason Kim's explaining it so deep is so that you would know what to ask for, if you needed to know, or what to report if you're doing a study. It's a recommendation, right?
Yeah, it's my opinion at this point. Yep.
It's a good opinion. I agree wholeheartedly.
All right, so let's change now. We've talked about intensity measurements.
Have you ever seen a paper without any pressure or intensity reportings?
Oh no, so the reviewer would never let that go by. But I did actually see a paper where they only reported the spatial average and they didn't actually have any temporal characteristics that they were reporting. It was just sort of the spatial characteristics, and it's not clear what you do with that number.
Yeah, and one more thing, Kim, I know that you would agree with this. A lot of people will make their hydrophone measurements without the skull and the actual preparation. So they're getting massive estimations of how much intensity and pressure they're getting at the focus. So
Yeah,
you have to be a skeptical shark out there when you're reading these papers. Except not for any of the people that are speaking for this course. Their work is amazing. We can vouch for it.
so we'll talk about that a little bit more. I think that if you have nothing else, then relating what your beam profile is that you measured in a scan tank is something. But you're absolutely right, because once you have a skull in there, it deforms, the beam will change, and as well as getting absorbed, but also then the shape of it gets changed. So it's really, and it changes from person to person and what part of the skull you're on. So yeah, absolutely right that you need to be somewhat skeptical of exactly what the intensity is across the skull. All right, well, let's talk a little bit now about highly focused transducers and gain, and then we'll move on from there. So this is something that we saw before. If you looked across the beam, then there's the near field, then we get into the Fraunhofer zone and the intensity comes up. And then there was an equation for what the pressure was along the beam profile. Well, what if we focus more? And we've talked about there's a number of different possibilities for highly focused transducers. So the Insitech brain system has an F number of about 1. There's the fibroid system built into the tabletop, has a much lower F number. There's the bone system, which is flat. It's a phased array, so you can curve the beam or curve the phases coming off of that so that you have a focused point. And then you can use a number of other possibilities. So you could use a curved system that has an angular array, or a round system that has, randomly spaced elements, for example. And of course, they're going to have different focusing. They're going to have smaller F numbers, as you saw with that system, or they maybe have larger F numbers, and then they'll have different beam characteristics. So one of the beam characteristics that we haven't talked about so far was the gain. And if we define the gain as the intensity at the focus, and then divide by sort of the intensity right at the surface of the transducer. And so then what we see is it's related in this way. So the larger the transducer, the more the gain. The smaller the radius of curvature, the more the gain. So in this situation here, where we had the same diameter on the transducer for these 3 different simulations, but all we did was change the radius of curvature, we see that there was more gain on the one with the smaller F number, the smaller radius of curvature. So that's one point to notice. Another one that's really important to notice is that as you increase the focal depth, as you go from a focal depth of 6 centimeters to 8 and 10, then the focal spot increases. It's just sometimes, you're just stuck with what your focal depth is in order to get to your target, but it's just one of those trade-offs to keep in mind.
Why are you, I forget why you're bringing this up now. Is this to say what kind of transducer you would want to use if you're trying to meet requirements, intensity and pressure requirements?
Well, we're talking about a little bit about highly focused transducers, and I have a couple more things to say about that. So just kind of introducing that concept.
Okay. I actually don't remember. I'm really asking. I forget why we switched between those things. It's a real
All
question.
right, so we're going to use a highly focused transducer. We're going to cause some thermal ablation. And you can see in this piece of meat, ex vivo, a number of different focal spots here. And some of them are bigger and some are smaller. They're all sort of, I don't know if you could say it's a grain of rice or a cigar shape. The tissue gets stiff and white. It becomes dry and desiccated. And this is very similar to, that situation many people are familiar with, where you take your roast or your pork chop and you put it in the oven, it comes out and it's stiffer and whiter than it was before it was cooked. So that's just what we're seeing here. The tissue becomes stiff and white. It's actually kind of interesting when you're thinking about an MR imaging method for looking at this, that the fact that it becomes less watery means there's less water protons to be imaging. And my feeling is that many of those get pushed out, and then you end up with a bright ring from what those water protons that get pushed out. But anyway, that's a little beyond what we're going to talk about.
I have a good question. Well, complimenting my own question. If you have live and healthy tissue around the point of tissue destruction, does the brain usually clean that up pretty well, or is there scarring that's pretty heavy? Has anyone looked at that? I guess it depends on
Um,
fat size and how much blood can get to it, and macrophages and things like that.
Yeah, I don't think you tend to see scarring forming in the brain. I think that the body will come in and clean it up, and then you either get just like sort of a little pocket of fluid that would be bright on T2 weighted images, or maybe it just kind of disappears altogether. Okay, so one of the nice things about focused ultrasound is that you can have very, very sharp demarcation between the area that's ablated and then the area that isn't. A little hard to see here, but then when you look on the histology, it's very obvious. So this is an H&E scan of thermally ablated prostate tissue. This is the normal prostate tissue up here, and the normal appearance is you've got individual cells. The nuclei are the darker purple, and then the cytoplasm is the lighter purple. And then you have normal cells all around the glandular space, which is right in here. So those are normal looking cells. And then there's a very sharp line. We go from normal looking cells to cells that are all broken up right here. And so that just really shows you the power of the focused ultrasound for tissue ablations. You can have just these really sharp lines in thermally ablated tissue. Okay, yeah, and we've talked about lesion dimensions as well prior to this. One of the points I wanted to make also is that oftentimes you have, let's say this is a fibroid right here, and the focused transducer is inside the tabletop, and it's focusing to a point deep inside, and then there's that cigar-shaped lesion. And it's small, oftentimes, compared to the area that you want to treat. So if you wanted to get a large volume treated, then you have to do multiple of those. And so this is now showing you a cartoon where we do multiple, where we sort of scan around one after another. If each one takes about 20 seconds, and then you have to wait for a minute between them, now maybe you've waited 10 minutes to do something of a small volume like this. Then if you wanted to increase the volume, you might increase the volume in that plane, scanning around and making more in that plane. But if you wanted to have another plane, then you have to come forward towards the transducer, and you would do the same thing again. You always want to ablate farthest from the transducer and then move towards the transducer, because when the tissue is ablated, the absorption increases. There'll be more attenuation because there's more absorption. And so getting past a thermal lesion to an area that's past it is harder to do because of that attenuation's gone up. And you may not get a very good focal spot past a thermally ablated area. So typically what happens is you go farthest from the transducer and then move forward towards the transducer.
And Kim, you mentioned 20 seconds for each of these ablation areas. What's stopping us from using higher intensities for shorter periods, just to make it faster in case the patient's moving? If you could do a really quick scan.
Yeah, that's a good question. So there's certainly the power output on the transducer. And then, going for a certain, longer time period is an easier way to get more energy in. That's probably the main reason. All right, so let's talk a little bit about optimal frequency. So there's competing factors here. Of course, when we're talking about a tissue ablation, such as in soft tissue, then our attenuation coefficient is dominated by the absorption term. There really is, the scattering in soft tissue isn't really all that great. The competing factors are that we want to have high intensity getting to the target. So that means we want our attenuation in the beam path to be low. And it might imply that we want a low frequency. However, at the target, we want to have high absorption so that we have a high temperature rise. And that might imply that we want a high frequency. So there's these two competing effects. So what do? Let's look at it a little bit more carefully. So the intensity that's reaching the target is, of course, got this factor here. And so what we see is the intensity reaching the target decreases with the frequency. So the attenuation, of course, is dependent on frequency. And so again, that implies that we want lower frequency to get to the depth. But the trade-off is that the absorbed power is also dependent on frequency. And so this has the frequency dependence in it, but then we can take out the frequency dependence and put it in right there explicitly. So this is a constant, and then there's the frequency dependence. And now what we see is that in order for the absorbed power to be high, we're going to want a higher frequency. And so if you actually evaluate this equation now as a function of frequency and depth, then you see that for the very small depths, then the absorbed power is going to increase until you get to some optimum, maybe about 5 megahertz. And then as you go to more deeper and deeper into the tissue, the optimal frequency is now decreasing and decreasing. So you can actually figure out, well, what's the optimal frequency? What you do is you say, you want to find the maximum right here. And the way you find the maximum is that you take that equation and you take the derivative and set it to 0. So that's what we want to look at, is where that derivative is 0. And if we do that, then we find the optimum is related in this way. And so the optimum is going to fall off with 1 over the depth.
If you were to do this for skull and brain, would you use the attenuation constant based on the average as you move across skull and across brain tissue?
It's a little more complicated for the skull, because we're going to have to take into account the fact that the beam path is not just the absorption, but also scattering, and scattering is really big. So we're going to have to use the skull parameters for getting along the beam path, include the skull for the beam path. But then when we're talking about the focal spot itself, then we're just worried about making sure that the absorption is high. So it's a similar thought process, but it's going to be a little bit more complicated. Seems like that might be a good homework question.
Yeah, I was thinking that. Not that I have to do the homework, so it's very nice, but you have to make it.
All right, so let's go on to our last topic, which is kind of a fun topic, because what this one does is going to bring in a lot of these same concepts that we've talked about so far with respect to grading lobes. All right, and we've talked about this, different types of therapeutic transducers. And there's no magic here. All the same issues exist. There's going to be side lobes that are going to be kind of small, but there's also going to be these large grading lobes. And we want the fact that there are grading lobes is going to impact our element spacing, and we're going to want to reduce the grading lobes. But just given a specific transducer and the fact that there may be grading lobes, then let's look at the effect of those. There was a nice paper that explained this and sort of demonstrated this really nicely by Alison Payne. There's been a number of other publications that date back a few decades about this, but this was just kind of a nice publication. And what they did was they were comparing the situation where they had a phantom here, and they were electronically steering, so going through a 3x3 grid, one after another, electronically steering, and comparing that to the situation where now their transducer is hooked up to a system that could move it for sonicating the same locations. And this is what they found in the situation where now what they're doing is they're plotting the mean thermal dose across for those the 3x3, and the mean thermal dose in the phantom as a function of the distance from the transducer face. So their target is out here, and they're looking at the near field as well and plotting the mean thermal dose in the near field. And what they see is that when they do the electronic steering, they have more thermal dose in the near field than they do when they have the mechanical steering, which is really interesting because you might think, well, why on earth would that be different?
Why?
Right?
Why would that be different, Kim?
Why is the near field heating larger? Well, there's two reasons for that. One of them is that if you're just electronically steering, your transducer is staying in the same place, and so there's more overlap of all of the beams. If you're actually mechanically steering it, then you can see that you're sort of spreading out the power as you move the transducer. So that's one reason. The other reason has to do with those grading lobes. So remember we talked about the presence of the grading lobes and how they, as you steer the beam to the side, then both the main lobe and the grading lobes are kind of going around this oval as you see here. So you steer to the side. And so what's happening here is that as we steer to the side, that grading lobe is increasing and it's putting more energy into the near field. Right, so that's exactly falling out from this picture, is that we steer to the side in order to get to the target. That near field adjacent to it is getting heating just from that grading lobe as it's increasing. If you're mechanically steering, then you're always pointing straight out. These grading lobes are staying relatively small. If you're electronically steering, now the grading lobe's going to increase. And then the main lobe might be decreasing. So that's the reason here. Why is the main lobe amplitude smaller? Well, that's the same thing as that main lobe is decreasing. I put these slides in just to kind of review the math. I don't think we need to go through these. I'll just jump to the end result. And that is that because of the way that the multiple elements are set up, that you end up with your little sync pulses over here, and they're following the amplitude of an overall sync modulation. So when you steer to the side, that main lobe is going to decrease in amplitude. So that's explained why you had less energy there and more energy there. So it really was a little suboptimal in some sense. You don't really want the energy here. You know, electronic steering is just so nice to think about. Well, you don't have to move the system around. You don't have to deal with a system that has to be moved around like the one that, you know, one of those systems I was showing you, you could just strap on, but then it's electronically steering.
Can you remind us why in neuromodulation we would want less energy in the near field?
Well, anytime that you're worried about what's the effect at the target, then you don't really want to be in the situation where your near field is very close to having the same intensity or the same effect. Right, you want to be very clear that your target and the focus has a much bigger effect than everywhere else. And in this situation, well, maybe it's a little less clear.
I think one of the students mentioned this in the questions, but if you can get and you mentioned this, you can get your grading lobes further out, more towards 90 degrees, it's more likely they'll hit the skull, which is probably less of an issue than hitting off targets in the brain. Is that right?
Yeah, I would think so.
The jury's not out on that yet. Don't quote me, but we think.
Okay, well, let's just sum up. We've talked about intensity measurements and especially ISPTA and how to calculate ISPTA. We talked about the gain for highly focused transducers. We've talked about our optimal frequency and how that's going to get more complicated when we talk about the skull. And then in the next lecture, I'll talk about, I think it's really important that we start talking about how to model the temperature. And so that's what we'll talk about next time. All right. See you later, Keith.
See you, Kim.